In this example, we will find the second degree Taylor polynomial for the given function centered at a equal to 9 and use it to estimate the function value at 9.9. Since I'm looking for the second degree Taylor polynomial, we need two derivatives. So the function is 24 x to the 3 halves. The first derivative is 3 halves times 24, which is 36. Then x to the 1 half, exponent goes down by 1. The second derivative will be 18 x to the negative 1 half. Remember that our next step is to plug in the center value. So then we plug in at a equal to 9. If we plug in a equal 9, that's 24 times 9 to the 3 halves, which is 648. That's 36 times 9 to the 1 half, which is 108. And that's 18 times 9 to the negative 1 half. 9 to the negative 1 half is 1 over the square root of 9, which is over 3, so 18 over 3 is 6. All right, so then, remember our next step is to divide by n factorial. So we want fn at a over n factorial. So that's 648 over 0 factorial, since that's n equals 0, which is 648. That's 108 divided by 1 factorial, which is 108. And that's 6 divided by 2 factorial, which is 6 over 2, which is 3. Which means that I can write down my Taylor polynomial. P2 at x is C0, 648, plus 108, C1. Now here's something that's a little different, so remember to be careful. If we center at a different point, that means we've shifted our entire polynomial over to x equal 9. What used to be at x equals 0 is now at x equal 9. To shift a graph over to x equal 9, rather than placing x, we need x minus 9. That shifts everything over so that x equals 9 is the main point. Plus 3 is our final coefficient. And the same thing happens there. Rather than x squared, it's x minus 9 squared, since we've shifted our polynomial over 9 units. So the only difference here is we plug in 9 instead of 0, which we had been looking at before, and then we're using x minus 9 in place of x when we write out the polynomial. So now if we estimate f at 9.9, I would like to say that f at 9.9 is approximately a Taylor polynomial at 9.9. That's the whole idea of Taylor polynomials. So if we plug 9.9 into this, P2 at 9.9, I get 648 plus 108 times 9.9 minus 9 is 0.9 plus 3 times 0.9 squared, which is 747.63. So that's P2 at 9.9. If I actually calculated f at 9.9, that would be 24 times 9.9 to the 3 halves, which is 747.59. We find a very good estimate using just the second degree Taylor polynomial. But the key point is that I could calculate that 747.63 using only addition. Where we added and multiplied, but multiplying is addition. So this step here is something that a calculator or computer can do. A calculator or computer cannot do square roots. When I plug this into the calculator to get this value, it's actually taking a longer Taylor polynomial approximation and using that just to make sure that we have something so that the error in the estimate is smaller than the decimals that we can see on the calculator. And that's how a calculator actually uses Taylor polynomials.